No. Because technically,
Okay, this is recorded now.
technically, the qualifier should not even be, it should not even be over quantum two.
Oh,
The qualifier should be all based at Griffith level.
okay. Oh, John?
Technically, Sairway and Griffith, or Rex Thornton or whoever it is, but it's all junior, senior level quantum mechanics.
I see.
And it did come out of the material itself came out of Griffiths. The notation, not so much. Right?
Gotcha. Depends who is making the qualifier. Do you guys get to know who makes the qualifier? Or?
Not right away.
I mean, I also don't know. I'm not involved in this at all. But if I'm not wrong, traditionally it is not necessary. But traditionally, there is one professor associated with each qualifier, so their bias about the subject comes into the picture. Yeah. So I'm not involved in qualifiers at all. That's some of the advantages if you want, then I don't know how to do that work.
I know that the E&M qualifier is definitely junior, senior level E&M.
By the way, does this course help with the qualifier at all? No.
We haven't gotten far enough into the course. I think at this point in time, it would probably help more. But in September, the majority of the when we got into the magnetic dipoles, that wasn't until second semester.
That's correct.
And so, but there was a rotating sphere, charged sphere problem on the qualifier, and it was more you had to reason your way through it because you didn't have a calculator. You had some formulas. And so, with some of the professors, if you explain your reasoning, that's sufficient.
Okay. Thanks. Thank you.
The nice thing about that is I found out what the initials EPR stood for.
What is P? The R is Rose Pedal. So next, so if you guys did you guys enjoy reading it, or I don't expect you guys to have read it and completely understood it in overnight unless you have thought about it before. But was it useful? Just being aware of the.
I have to be honest, I skimmed through apparently because I knew Einstein's issue.
Yeah.
It's
hard. I think even so the logic of that. At least I think it's hard. I don't know. I shouldn't think. I personally think it's hard.
Well, I have a question about that then. The EPR paradox. So, Pauli's exclusion principle says that no two electrons can have the same base energy state, right?
Yeah.
So why didn't anyone consider that idea that, maybe people have, but I didn't see in their argument specifically about the Pauli exclusion principle where electrons would have different base energy states. So instead of, when you excite some particle and then it comes back down to its base energy state and splits, let's say you have a positron and an electron, then the life of the positron is short, but wouldn't its energy state have to be different than the electron state? So
what's the question? So specifically, you're saying why was Pauli exclusion principle not used in formulating the paradox?
I guess like the transfer of information like instantaneously. instead of like it being an instantaneous transformation, the information is slightly different because the base energy state is different. So why couldn't it be more of like a deterministic, like information carried inside? If no two electrons have the same base energy state, then they carry different information essentially. So like imagine a fluid. I don't know how to explain it exactly, or I don't know how to formulate the question maybe appropriately. But I think they use the idea that, if it's there's two forms or two different ways that you could have a solution: local hidden variables or instantaneous transformation that would be faster than the speed of light for information. So that's kind of the paradox, right? And Einstein was saying like, no, it was more like a left-hand glove, right-hand glove thing, where the information was contained in itself. It was always either a left-hand glove or right-hand glove. And so once you measure where the particle is, say you measure the left particle, then the right particle, you can only know the measurement on whatever, if it was spin up, then it's spin down, but you can no longer measure the spins with respect to, let's say the axis of X is a momentum axis. So you lose some bit of information. But what if that information is stored because the base states for those particles is actually different? It's not the same. So really it's whenever you have those two particles split from that one action, making them quantumly entangled, because they can't have the same base state, then certainly their information is different. So there is different information there. Otherwise, then you're also violating Pauli's exclusion principle, right?
I don't know. Simplest way of saying it. I can tell you what my simple understanding is, but I think you said it. You seem to be saying the same thing, so I'm not sure how much it will help, but I can tell. Will it help if I say a few words?
Yeah.
Don't cross-question me too much. Okay? Einstein couldn't answer Bohr, so who am I? So, let's try. I think so. Okay. So quantum mechanics says that, let's say there is only two states, right? Left and so first of all, quantum mechanics says there is left or there's a two-state system, left or right, right? So if you measure, there's a 50% chance of left or 50% chance of right. Now you construct a state which is two of them, right? So let's say there are two objects, which could be either left or right, right? We don't know. But we do know that we construct the state so that the sum of them has to be zero. One is the left, one is the right. So conservation of spin, let's say, the total spin is zero. It could be either one of them, but total spin is zero. Right? Total is left plus right. Right? So if one is left, the other has to be right. But we don't know which one is which. Right? So that's the state. Now you do an experiment where you very carefully take this away. No disturbance at all, right? So you take it away, and they're, let's say, in two galaxies, right? Hypothetically speaking, they're in two different galaxies, and now you make a measurement. Right? So remember, this is probabilistic. You make a measurement and you learn that this is left. Right? Because this was total L plus R to begin with, this cannot be anything other than R. Right? You immediately, in an instant, you made this right. So you performed an experiment here, and you got a result instantaneously, unless this information went with some quantum mechanics does not have any speed of light there. So instantaneously this became right. And the point is this instantaneous Is this violating causality or not? One would say, and now if you again make the measurement, again you will get left, again you will get right, that's perfectly fine. So sometimes the claim is that you're not really passing information because you went only once there, right? For passing information, you have to do more than once, isn't that correct? I'm not sure about that. Right? I think you can get away by saying that, okay, you're not actually, no, actually, I would say there's information going right. Is that right? Would you say that there is information going in there? Yeah, there is no information because to begin with, you didn't know what was what, right? You still don't know what is the left or the right. So to ask that again, you have to again make a correspondence, and that probably is causal. But as of now, this is the issue here, that is this causal or not? That's quantum mechanics violate causality. And now you can build things out of this, make a paradox out of this. But as far as I'm concerned, that's all that is. And which is true in any conserved system. You can take any angular momentum conservation. Let's say you have a Earth and Sun system, and let's say it was possible that you could separate this out sufficiently, and you make a measurement of Earth's angular momentum, you know the measurement of Sun's angular momentum. Yeah, so that's in a sense instantaneous. But there it is not, there it is deterministic. That's the catch there. So
Yeah, so I was just thinking maybe the better way for me to say it is if you go to a lab and you create a positron, right?
Mhm.
It's, you know, it doesn't last for very long, but it can't have the same base ground state as any other electron in the universe, right? It has its own unique ground state. So why couldn't you know, the universe know that when you make a positron that it can't have an already taken ground state? So carrying with it some piece of new information which would determine, you know, which way, if you took a
You're
measurement.
suggesting, if I understand you correct, because positron is a fermion, it has a specific state of its own relative to every other fermion in the universe.
Yes, and it must have a different state.
Yeah, but that's very tiny amount of difference. Like as far as the positron you are considering, unless you interact with the other positron too closely, they're pretty isolated. They're pretty much free. It is correct you're saying that, but the difference between the state between the positron here and another positron in your neighbor's lab might be unmeasurable. Like it might be different by so minute an amount that it is practically the same. So that doesn't help much, I suppose, unless, yeah, between the two positrons that you have in your lab, maybe yes. Does that?
I guess yeah, kind of, but I feel like they just have to be different, you know, no, regardless of the amount that they're different.
True, theoretically they're different, but practically, if you are different by 10 raised to minus 35, it's practically useless, right? You see what I'm saying?
Yeah. Yeah. I
Like
see
you're
what you're
saying,
saying.
yeah. Maybe, yeah, yeah, but think about it. I would say, yeah, this discussion can go very long, and
Yeah.
I myself have difficulty grappling with the whole thing. So, pilot waves. No, I'm still with the traditional quantum mechanics. Yeah, but yeah, 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 sure, I'm open for all this. Okay. I did post a homework, which is not listed here. So there is a homework 9. That's due on next Thursday. So Tuesday we don't have class, right? 22. So no. April 20 Tuesday, and I won't be available on the campus either, so I really have to be about. So let's go. No office hours, but I don't have office hours on Tuesday actually. Final exam, May 6th, Tuesday, and yeah, I said this is in class, mandatory kind of. So.
Moses again?
No, it is not Moses. Yeah, this is something. Yeah, it has something bureaucratic, but nothing to do with any. So it's some bureaucracy. I don't know. Randomness. Yeah. But I don't think any of you get affected. None of you at all. It's nothing to do with the class. But yeah, it has the reason. Yeah. Okay. So we have to do radiation. So yeah, so we did statics, electrostatics, magnetostatics, and very recently we combined them all together and introduced time. And we talked about a charge that is uniformly moving with uniform velocity. And we saw that it gets tricky. It gets a little work to evaluate that. And in an exact sense, it becomes very difficult, almost impossible to do those integrals. So we, in the absence of those exact theories, we have to deal with some approximations. And even though I say approximation, this is not really an approximation, because we will construct a theory or construct a configuration where we will say that our boundary conditions are like this. And that's what we will call radiation. So it is an approximation in the sense we are not exactly solving the whole thing. Instead, we will be interested only in the electric and magnetic field at very large distances. So radiation by definition would be, you have an atom, let's say in your lab, it's a small sample, typically lab atoms are 10 raised to minus 10 big. In a small sample in your lab, and you're measuring 1 meter away, even if it is 1 centimeter away, 1 centimeter and a nanometer, that's a billion times distance. So it's infinity as far as our approximations go. So there will be a radiation emitted by the atom or anything, or for example, or if it's a radio wave, then it's an antenna, and you will observe it very far away. And in that far distance approximation, whatever you get will be called radiation. Now the question comes, before that we have studied electric field and it's 1 over r square dependence. 1 over r square dies off very quickly at infinity. Typically there is nothing surviving there. And that won't be the radiation field. Radiation by definition will be 1 over r. Okay, so electrostatics has 1 over r square. And radiation, as you will see, will be 1 over r. So that's a signature of radiation, is that it is a 1 over r dependent electric field, not potential. Potentials are 1 over r, but this will be strikingly much more stronger than 1 over r square. So even at infinity, it will survive. Mostly, remember, energy is square of electric field, right? E cross B is momentum density. Half epsilon E square is energy density. So they will survive. So they will become 1 over r square. So that's a point you want to take home. Electric field due to radiation and magnetic field due to radiation will be 1 over r dependent. That's the main point. But we have to derive the whole thing, and I'll try to do it. And one day, but already I have lost half an hour, and I have to finish a little early this time because I happen to be speaking today. Yeah, I speak on something on wheels. Yeah, in what direction does the wheels friction work on the wheels of a car? Forward or backward?
Forward.
Forward.
I don't remember. It's counterintuitive. Though.
Well, the friction pushes.
Friction pushes forward because if you rotate the wheel in the direction, say it was your hand, and you pressed your hand on the concrete, the direction of your skin would be the direction that the friction goes. So therefore, it would have to be forward.
But I thought friction was necessary for rotating things, right? So isn't there a counterintuitive feature there? If there is, the friction makes it roll, right? Is that clear what I'm saying? If you think of rolling, you need friction, correct?
Yes.
Like I'm confusing you guys. I think you guys are correct in saying that friction is forward, but it's not a complete answer.
You need friction to start rolling, but once you overcome like that static friction, begin your roll, then the tires moving on some surface works against you, right? So
yeah. Okay, attend my talk. Yeah, yeah. Let me proceed so that I don't waste more time. Here, waste half an hour. Okay. Yeah. Yeah. Again, not a. It's not necessary since I have this. I'm a course instructor. Attending the talk is not necessary. It's not related to this course. You won't lose anything. It's just an advertisement. Nothing at all related to that. Yeah. So just to finish the answer, I think the back wheels have backward and front wheels have forward. If it's the front wheel drive, so there's both wheels acting on it. So that's it. Okay, radiation. Right? So we're going to talk about, so there are charges. So this is moving charges here. So we will specify the motion of that. And remember that this doesn't have to be really an atom. I said atom emits and observes. And we can even have a radio antenna. Radio antenna. How do you communicate using cell phone? Right. Notice there is a charge that is actually moving inside your cell phone, and that motion creates an electromagnetic wave that's picked up by another antenna. So that's sort of. And I should also say, I said, yeah, 1 over R is the radiation field. One more is that if you accelerate any charge, it will radiate. Okay, by radiate, I mean it will emit an electric field, which is 1 over R formed at infinity at very large distance. So 2 points to take home. One is that it is radiation fields are 1 over R dependence. And second is that anything that accelerates, any charge that accelerates has to emit radiation, and radiation involves energy. And this is what triggered quantum mechanics, right? Because, and why did it trigger quantum mechanics? What was the connection between radiation and quantum mechanics? Or what started quantum mechanics? What was the big deal? If you go back historically.
The electron would orbit into the center of the nucleus.
That's correct. So they started seeing this radiation from atoms, basically all the color that you see of an atom, copper is blue, all that could be explained using atomic levels. And then Maxwell said that if an electron is accelerating, it has to radiate. And then you say that anything that goes in a circle is accelerating. No, you don't have a choice. And if it is accelerating, it has to radiate. If it radiates, it emits, you're losing energy and it will collapse. But then you would argue that, oh, maybe that collapse is very slow. It takes 1 billion years to collapse. But you can make this calculation. That will be part of your homework. I think that is part of your homework. Or maybe not, I don't know. I give this at undergraduate level. So you can actually calculate the time it will take for it to collapse from a finite radius to 0 radius if you keep emitting energy out, and it will come out to be nanoseconds. So all these atoms should be stable only for, they should survive for nanoseconds, then they lose their energy and the atom is gone. So the electron goes into the proton, sort of. But they're stable, we know that. So we don't know how to fix it. So quantum mechanics is, in a very blunt way, is this fixing. It's not a clean way. You just force it, saying that it cannot go down. Since experimentally it doesn't happen, so you come and say that we won't let it happen, and that's your new theory, where it doesn't allow it to go below the ground state. So then you build some rules to do that, and it turns out to make other predictions out there. So that's the way quantum mechanics came up. Okay, so that's your charges moving around in a sense, and you make, so that's your R prime, right? In our language, we would say that's R prime, and you make the observation somewhere very far away, that's your R. And now there is a time also involved, so there is a T prime here, and there is a T there. And by radiation, we would mean that T minus T prime will have to be very much less than R minus R prime. I should say, what is T prime? T prime is some characteristic frequency of the source. Like if there is a source, for example, if there is an electron going around an atom, it is a time period. So there is always a signature time you can associate with the quantum. So that's what will be the point. So let's do this more in detail. So any configuration like this, our electric potential is phi of RT is equal to 1 over 4 pi epsilon naught. We have dt prime q R prime and z. Right, that's your electric potential and magnetic potential similarly is in the board. Yes. Same thing, just that it is current density that shows. Oops. And we did this integral exactly for a particle that was uniformly moving. Just to give you a feel for what is going to happen if there was an opposite limit, right? We are talk about radiation approximation where this is very large. If there was an opposite approximation, then this can be neglected if this was very small compared to that. Then we have t minus t prime. Delta function of t minus t prime would allow you to do this integral and replace this t prime with t. And this was encountered last time also, and we said that that's pretty much static. It's an action at a distance. Right? And Luke, you asked at that time if there was a way to see that this was actually an action at a distance. Remember that if whenever you have a light cone, and if you're a time-like particle, then it is causal. And if it's a space-like, that means it is simultaneous, like it can happen instantaneously. So you just have to show that the distance that we have is space-like. And there is a homework in your new homework, there is part of it where you show that it is actually light-like. So actual radiation happens light-like because it is light that is taking you from one into the other. So in your, to answer your question, you just have to show that it is space-like. So that's a formal way of answering that question. Yeah. Okay, so that will again take us to that, but let's do radiation approximation here. So we want to talk about the situation where this is very large, and let's pretty much say we will use far field approximation. This is an added approximation to the radiation approximation, but most of the time it is okay. Far field approximation. Where does it not work? Approximation. Where does it not work? If you're actually building a radio antenna and you have your receiver right next to the radio antenna itself. In that case, this far field approximation is not a good approximation. So the far field approximation is when you say R prime, R and R prime, so R prime is pretty much close to the origin and R is pretty much infinity. In that case, you have R minus R prime magnitude is equal to square of this, right? So this is square root of R square plus R prime square minus 2 times vector R dotted with R prime. We want to keep R to be very large compared to R prime in the far field approximation. Pull that out. You get 1 plus R prime over R square minus 2 2. So this will be R hat dotted with vector R prime over R. This is a unit magnitude quantity. This is 1 over R. This is having a, if you talk about magnitude, it is R prime over R. The third term is 1 over R. Second term is 1 over R the whole square. So when it is very small, this is actually negligible. I can drop that. Then I expand out the square root as a series expansion, and I get 1 minus half of half R hat dotted with vector R prime over R. And there are higher terms there. So that's the same as R minus R hat dotted with R prime and higher terms there. In the same approximation, there is one more term here sitting there in the denominator, and that we will not need to even go to the next order. It will be sufficient to just approximate this to 1 over R. There will be a next term, but it turns out that since if we keep this, we just only need to keep the 1 over R. The next term is, we are interested only in the leading contribution. That's the idea. Okay. So with that approximation, let's proceed to calculate the electric potential. So substitute this in there. So you have electric potential is equal to 1 over 4 pi epsilon naught T prime First of all, I can actually complete the T prime integral even before the approximation, right? So let me complete the T prime integral. dq r prime and this is rho of r prime. T prime gets replaced with T minus right, that should be okay. I just evaluated the T prime integral, no approximations yet. Now I do the radiation approximation. This is d cube r prime. Charge density r prime T minus, this is r over c. That's coming from there, plus r hat divided with r prime over c. And in the denominator, I simply replace this with the r. Right. That's the two approximations. So I'm interested in the leading contribution.
Sorry, is that both approximations together or just the far field approximation?
It is mostly far field approximation. Okay. It is both actually. Okay. Why is it both? Because it seems like I have only done the far field, right? How do you explain this? No, it is both because there is a time involved, right? I have neglected something relative to time. Correct? I have neglected a, let's say this term related to time. So if, for example, there was t, if there was this term here, which was r prime over r square, and let's say there is a r, right, r over c. Correct? I have neglected this compared to that. Okay. So I've assumed that this is what happened? How? I'm not sure. Because I have neglected this compared to this, and yeah, where is my T prime? Where did my T prime go? I have to go back, and this step is clean up. So your question is, where is my radiation approximation sitting here? You should go back and do this approximation here, but then you will say that's a cheat. That's an artifact of the mathematics. I'll get back to you. I don't have any immediate answer, right? So let me try to get back on that. So the question Nuke is asking is that, is this not just far field approximation? And where is the radiation approximation where the distance is very large compared to the time showing up? And radiation involves, in fact, true radiation involves that far field is just a convenience I'm using. So if you guys allow me anyway, it's a very basic thing pending there. So if I proceed, try to answer that later. Notice that is a significant, this is a significant approximation because R completely comes out. That's your electrostatic potential. Is that complete? Or this is R prime? And this is d cube R prime. and charge plus R hat dotted with R prime over C. And you say that that's integral of charge density. What is integral of charge density? Overall space. This is overall space. It should be charge.
Total charge, yeah.
So that should be total charge. And you have nothing left then, right? So it's Q over R. At the end of story, that's electrostatics. But that cannot be right? That's wrong. Why is that wrong? Because this is not, there is an R prime here and there is an R prime there. So when you're integrating, this is not a straightforward integral. Like when you say integral over charge density, it is at each point you get a contribution there, right? But this is R prime is sitting inside of the time. So it's a convoluted statement there. And we will talk about that a little bit later on. So this is not equal to charge Q. In fact, it will contribute. There will be a contribution more than charge Q in there. Okay, that's your electric potential, and we have vector potential similarly, same idea, nothing different, and is equal to mu naught over 4 pi 1 over R dq R prime. R prime P minus R over C plus pretty much the same statement except that now it is current density. Okay. Mathematically, it is straightforward from this point on, except that the calculations will be a little messy, but once we know the potential, we know what to do, right? Electric field is take the gradient of the potential, take the time derivative of A. This is new. Earlier we used to have only gradient, negative gradient, but now this is this, and magnetic field is simply take the curl. Okay. So let's see how do you take the gradient, right? Just let me give a feel for what is happening. Electric field is equal to negative gradient of 1 over 4 pi epsilon naught 1 over R. And that is an integral of the cube. Sorry, not the electric field. I'm doing negative gradient of phi. Rho of R prime T minus R over C plus R hat dotted with. Okay, and there's a right also. If it was electrostatics, this gradient will act on this R to give you a 1 over R square, and that's all. But now there is more things it can act on. This can act on this R here. In fact, it can also act on this R hat here, right? So 3 places it hits. Okay. So first so this is clear when it hits here, you get 1 over R square. It's your usual electric field. But I'm going to point out that that's actually a higher order in the sense it is 1 over R square. You will try to get a more powerful term when it gets this, and that will be the point. And we will neglect that. Okay, because it's higher order. We have already dropped higher orders. And so first of all, there is a term which is when I take the negative gradient, it becomes positive, right? So there's surely this term 1 over 4 pi epsilon naught r hat over r square, right? That's your electric field due to point charge times your whole quantity in there, prime but I want to hit this also. Okay, so to hit that whole thing, I'm going to define this whole thing as TR, the retarded time. I'm going to define retarded time as T minus R over C plus R hat divided with R prime over C. This will be called the retarded time. Okay, so I hit here and I have to hit all the R dependence inside of the retarded time. So how do I do that? So I have to take the gradient of something that is inside a function. So I'll use the chain rule. Right? So I'll do, so this is negative, gradient has to go there. So this is plus, let's say, or minus, let me keep the minus outside, 4 pi epsilon naught, 1 over R. So this stays intact. This is dq r prime integral, so that gradient can go inside in there. And how do I do this? So this is, first I take the derivative with respect to R, or the retarded time. Right. And then I take gradient of T of R. So that's a chain rule, right? Gradient of, I'm interested in gradient of this quantity here. Instead, I take the derivative with that function and that function gradient of that function. That's a chain rule. Okay, so that involves, what is this? Okay, so let's do that. And then I'll put that back in, and then we'll be good. Okay. So what is gradient of T of R? So that's gradient of T minus R over C plus R hat dotted with R prime over C. Okay. This is T, doesn't depend on the position, so that's 0. So this is minus 1 over C gradient of R and plus that is gradient of R hat, which is vector R over R, and this is dotted with R prime over C. Yeah. So this is, what is this? R hat, right? Remember the identities I try to. So this is always R hat, and what is this? Equal to? Unitary. Good. Yeah, good, very good. So this is equal to minus R hat over C. There's some operation there, so that is plus. That's a unit dyadic in the numerator over R. But I can hit the denominator also. This gives me minus of R, and then there is a minus 1 over R squared. I kill that unit vector there, right? So how do you do this? So it is r hat over r dotted with vector. Okay. So this is it. When it hits the numerator, it gives me a 1. When it hits the denominator, again you use the first identity, the gradient of r. So that's vector calculus. I've tried to do a lot of that before, so let's not go there. And it gives you all of this. Notice this is higher order than r. Already you see that. So this is minus r hat over c. So this is no dimension in r plus. Let me write this as 1 over r. And this is vector r prime. And let me write this as r hat dotted with r hat minus of r hat and 1 over c. And this might be familiar. Does this ring a bell? Whenever we get such construction. So this is in the direction of r hat, this is the direction of, sorry, this is in the direction of r hat, this is in the direction of r prime. So that's cross product, the double cross product that shows up in this situation. So that's minus r hat over c. Am I in the space? Yes. Plus 1 over r, and this is r hat crossed with r hat. So this is, sorry, r prime crossed with r hat, and the whole thing crossed with r hat. So this is back tab, right? So this is this, and this is these two. And there is a 1 over c. So that's the same as minus r hat over c. I can change this order, make it minus. So that's 1 over c times r hat crossed with r hat crossed with. This is a construction that will show up in radiation a lot. R hat crossed with r hat crossed with a source. So keep track of that. But in this case, it is not really relevant. This is going away, right? That's this is next to leading order. So we know how the gradient of the retarded time works. So let's use that in our electric potential. So if we use that in our gradient of electric potential, we have as gradient of phi I, the 1 over r square, no, so let's let me write that down. Copying this actually. dq r prime and rho r prime t minus r over c plus r hat dotted with r prime over c minus 1 over 4 pi epsilon naught 1 over r and and this is dq r prime, and now comes the gradient of the retarded time, so that's minus r hat over c minus 1 over c r hat crossed with and charge density, time derivative of charge density. So this is okay.
You're missing an R hat just in that the first line, the line above. There's an R hat outside the interval.
Oh, okay. Thank you. Yes. Okay. We want the leading contribution. Notice this is 1 over r squared. This is 1 over r squared. There's an r here, there's an r there. That's your leading contribution. Right. So there's a 1 over r squared, r times r 1 over r squared. This is the leading contribution, which is a 1 over r. Which apparently is 1 over r, then you would say that, oh, when I take the electric field again, I'll get 1 over r squared. No, this is electric field, sorry, I'm confusing. Yes. This is electric field, correct? So that's the electric field as 1 over r piece. But that's only gradient of phi. Now we have to do the other stuff too. So let me write this as minus. So minus and a minus becomes plus first of all. So it's 4 pi epsilon naught. 1 over r. Notice this is kind of electric field, almost. So this is, and r hat can come out, right? R hat can come out. And I'll keep the c with the time. R prime and d by dt c 1 over c times d by d r. Rho or prime. So it depends on the rate at which the charge density changes. That's how it works. We can also do the time derivative of A in a very similar manner because it's actually time derivative is easier, right? Because time derivative has just only this. Right? You don't even have to do it. So time, when I do the time derivative of A, it's much easier. A by dt is equal to mu naught over 4 pi 1 over r. Here the direction is inside the integral. This is d cubed r prime. Now c, so this is d by dt of j of tr. Whether I take the time derivative of this or I take the time derivative of this, it's the same. So I can write this as write d by dt of r of rho of as d by dt of rho of r prime t evaluated at t equal to t r. That's it, t prime equal to t. That's the same thing. That way, I will be able to do this also in the same spirit. Right? The derivative of this is identical to derivative of the whole variable. So I will use that to write this to be t equal to tr and t prime equal to. It's just a matter of notation at this point. I can also make this look very similar because mu naught is the same as 1 over epsilon naught c square. Put one c there and keep the extra c outside itself. So if you want, I can replace mu naught with epsilon naught also. Let's keep it as it is. Okay. Same thing goes through for del cross A also. Or let me first do the electric field. Now, if I combine these two, I have electric field, and The del cross A goes through pretty much the same way because that's also derivative, and its curl is just sitting there to act on or something. So let me pull this, put this all together. So this is B, which is del cross A, will be pretty much the same as this, except that there will be a cross product there. So this is mu naught over 4 pi. I'm using those approximations. So this is r hat over r crossed with d cube r prime and 1 over c okay, where PR is such complete story. And that's the same thing I've done. What I've done is, since there is a gradient acting on a potential, we got this approximation. It's the same idea that goes into the electric potential also, except that rho is J there. There is nothing else coming in there. And that's a vector. And in between you put a cross product there. So the same thing goes through. So that's a leap I have taken, but it's pretty much the same idea. There's nothing, nothing significantly different in there. Okay, is that visible? Intuitive?
Could you repeat that one more time?
Okay. Notice that I did del of phi, I did gradient of phi, got an answer. Gradient of A will be the same if I replace rho with J. Right. And probably epsilon naught with mu naught. 1 over epsilon naught with mu naught. Agreed? And if I want the curl in there, I put the curl in between J, R hat and J. So this will give me a R hat and a J for the next curl there. Is that clear? Because everything else, as far as the derivatives goes, it is identical. Is that clear? It's a saving time there.
Yeah.
Is there a confusion there? Dissatisfaction there?
I might need to convince myself that, but that's just because
Should I do it?
no, I follow.
Yeah, if you allow me to do that, okay, because then I have my B and E electric field that has 2 pieces now, because this has to be added, right? And then the problem remains to how to put those 6 together. So this is 1 over 4 pi epsilon naught R hat over R D cube R prime quiz to do that. Okay, just complete the repeat the steps to get that. So okay, and there's one more piece in here which is plus. Right? So this was plus and no, this was a minus, right? Oh, maybe did I mess up? Yeah, this was a minus, right? Because it's a minus. Minus. So the minus sign. So this is minus of mu naught over 4 pi times 1 over R and D cube R prime times E by D cube prime Okay, that's how far we have gone. What we are, so at this stage, what we are left out to do is that we will be able to convert these two into a single one. Right? We will be able to combine these two using some manipulations, and we will get the answer in terms of this. Notice current is velocity, right? Charge, velocity of current is, sorry, velocity of charge is what current is. And this depends on the derivative of charge density. That's acceleration. That's where the acceleration shows up. Right? This acceleration crossed with r hat is your magnetic field. Okay. And the next step is going to be, and so this is for next time, right? What we are going to show is that this is nothing but r hat crossed with d. Okay, we are going to be able to show that this is r hat crossed with d. So what we are pretty much saying is, as a summary, we'll come back and do this, that magnetic field is equal to r hat crossed with some source which depends on e by dt prime of j hat. Right, that's the source. Right, very integral of this if you want. So lots of charges moving around, acceleration contributes to this. Right? Magnetic field is like that, and the electric field is r hat crossed with the magnetic field. So let's get a picture of this. You have some charges around here, somewhere very far away. That's your vector r. Let's say this whole k is somewhere, it could be anywhere. It need not even be in the plane of the boat, so it can be out of the boat somehow. It is this. That's your k. So charges add up to give you a k. R cross k, let's say wherever they are, since there are two vectors, I can put them in a plane. Let's say they are in this plane. R cross k is my magnetic field. So that's R cross k here. This is my magnetic field. Good. Then I have R cross D. R crossed with D is my electric field. So that's my electric field. In such a way that E dotted with D is 0. In fact, since they are both given in relation to r hat, and they are all perpendicular, r hat, E, and D, they are all three perpendicular vectors, the energy, which is proportional to E square, will be exactly equal to B square. Where else do you see where the energy is equal in electric and magnetic fields and they're perpendicular to each other? Where else do you see that? Electromagnetic wave, right? So radiation creates electromagnetic wave. This is how an electromagnetic wave is created. Right? So that will be a characteristic we will see. But at this point, I'll stop early so that I can move to the classroom then. We'll come back and I'll finish that step there in between and I'll fill those steps in. Yeah. And we'll show that the energy is all the same, almost straightforward. Okay.
Can you explain the quiz again?
Oh, I was saying that fill in the steps to get this. Evaluate this explicitly. Like follow the steps that we did for the electric field and do that for magnetic field. And just attempt out it, remember that quiz is more of an attempt, but more you put effort into it, that should be useful for you, but it's not a mandatory. Okay. Aliyah, there?
Yes, I'm.
Questions, Aliyah?
No, thank you so much.
Okay. Shall I close the meeting? I have to run at this point. Bye, Aliyah.